Here's a worked example on vertical circular motion, another one. This is quite a lot trickier than the one that I've just done immediately before it. I thought it would be, the first one was a fairly straightforward one. This one's a much more difficult one. I thought you'd get a bit of a look at a range of things. So here's the situation. We've got a particle given mass hanging at the end of a 1.5 meter string, so it's hanging vertically down to begin with. It's projected horizontally with speed u, so it starts off going this way. And then what happens here when OP, so OP is the basic whole string. When OP is horizontal, it meets a small smooth peg at Q, where OQ is 1 meter, original radius of 1.5. What we've got to do is find the minimum value of U down at the bottom, right at the beginning of the whole thing, if P is going to make complete circles about Q, up at the top here, the small circle up here. Okay. So, actually, if you think about it, really, this is actually just a question of working out what speed we need to be at the horizontal position here when it starts its new, smaller circular motion. What speed do we need to have there to make it go all the way around? And remember that to make complete circles, when you're on the end of a string, the requirement is that at the top of the circle we need the tension to be greater than 0. Well, greater than or equal to 0, actually, strictly speaking. So really, yeah, this is a problem about this small journey here. But of course, in order to work out what speed we're at the horizontal position here, we need to know something about the journey from the bottom up to that top point. So it's a kind of two-stage process. We're doing one part of circular motion to find out something about the speed at the end of that bit, and then we're moving on to a different part of circular motion. And looking at that one. So let's have a quick go at this one. So I'm going to start by thinking about the large circle, and as always, or pretty much always anyway, I'm going to start by thinking about energy. So here we're going to be losing KE because we're going up the circle, so KE lost is going to be equal to GPE gain. So we're starting with a half mu squared. That's going to be the maximum amount of kinetic energy. So we're starting with half mu squared. And by the time we get up to the horizontal position, we'll have a speed of v. So our kinetic energy is going to be half mv squared. So the difference between those two tells me what the loss in kinetic energy is. And that's going to be balanced by a gain in gravitational potential energy. Now actually in this case this is very straightforward to work out. Generally this is the tricky bit, working out the change in gravitational potential energy because of the change in height. But here, because we're going from the bottom to the to halfway up, we're just essentially travelling vertically up by 1 radius. So this is a much more straightforward GPE gain thing. So all we need there is just mg, and it's just going to be whatever the radius is. I haven't started to put numbers in yet, so we'll come to the numbers now. Mass cancels out as it normally does. Be careful though, it might not sometimes, so just watch out for that one. Normally multiply by 2 here as well, and what we're trying to establish at this point is some expression for v, or probably v squared actually, in terms of everything else. So I'm going to rearrange this, multiply it by 2 and rearrange it and make v squared the subject of that all in one go. So we're going to end up with v squared equals u squared minus 2gr. And we know what the radius is actually. In this case, r is 1.5, so I can substitute that in, giving me v squared equals u squared. So I've got 2 times 1.5 giving me 3, so u squared minus 3g. So now we've got an expression for v, or v squared anyway, at the beginning of the small circular journey. So I'm going to start working on the small circle now. And with the small circle, we want to work out something about, we want to find something about when it's going to make a complete circle. So we need to be thinking about this in terms of a sort of generalized angle around the circle, and inspecting what it's telling us, so that we can then go on and find out about this condition for it to make a complete circle. So let's start working on the small circle. Sorry about the clearing of the throat constantly. Small circle here. Again, we'll look at the energy things with same sort of principles as we had in the large circle here. So I'm starting off now. My starting speed is v, so I'm going to have my my starting kinetic energy is half mv squared there. I've labelled up the speed up here on the at a general point in this small circle. I've run out of my normal u's and v's at this, so I've just randomly picked another letter there to use for the speed there. I've called it y, just so that I'm not repeating the use of the same symbol in different places. So I've got as my loss in kinetic energy now, I've got half mv squared minus half my squared. And that's got to be balanced out by a change in the gravitational potential energy. And now this is where we need to be slightly careful with our change in height, because I'm going to be looking at a general point around this circle. Let's say we've got an angle of theta in here. In there, I can't quite squeeze it in because the diagram's turned out rather small by the time I've got to that bit. So I've got an angle of theta between the radius, the string essentially, and the horizontal position there. Normally we use angles against the vertical, but it just seemed easier to me to look at the angle there in to the horizontal. And so that might change the way we approach this one. So I'm being a bit cautious about this and just being careful here. So change in height, we're starting at the horizontal position, we're going up to this position. So our change in height is just the vertical part of the right angled triangle that we could make down here. I hope you can see the mouse moving around that right angled triangle there. So this is our radius of the small circle. Well, that's 1 meter less than the original length of the string, so that must be a 0.5 radius. And so the vertical height there must be 0.5. Now it's opposite my angle theta, which is down here, so that must be a sine theta. So 0.5 sine theta for my change in height there. So my change in gravitational potential energy here just becomes mg times the change in height, which we've just decided is going to be 0.5 sine theta at a general point around that small circle. Okay, so again, mass cancels out, that's all nice. Multiplying by 2, blah blah blah. So we've got something which goes now v squared minus y squared equals, so I'm going to be multiplying by 2, and I've got this 0.5 here, so they're multiplying by 2, and that 0.5 there are going to cancel each other out. So I'm just going to have v squared minus y squared equals g sine theta. Okay. What I'm particularly interested in is the speed at some point, because I'm going to be next looking at my forces as well, because in the condition for the complete circles I'm interested in things about the tension. So I'm moving towards thinking about my forces. I'm going to be using mv squared over r, but the v in this case is going to be what I've now labelled up as y. So I'm thinking about rearranging this equation to make y squared the subject of that. So I'll just have that now as y squared equals v squared minus g sine theta. But I've actually already got an expression for v squared from the first part of the work. So now I can get y squared in terms of u as well as theta, at least anyway, by substituting in the expression above for v squared. So now I've got y squared equals, instead of my v squared, I can now have u squared minus 3g. And then I've now also got to put on this minus g sine theta from this part as well. Okay, and then I think I'm ready to start looking at the forces involved. So I'm just going to do a Newton's second law part here on the small circle. That's basically just an F equals ma, thinking about it radially. Let's have a quick look at the forces up in the diagram here. So I've got T going directly in towards the centre of the circle, so the full T. Now my weight in this part is adding on to that T. Often we're in the bottom half of a circle and we're subtracting that a component of the weight there, but now we're in the upper half of a circle, so my weight, or at least a component of the weight, is adding on to that T force. And the component that I want is going to be the sine theta component. You might need to just convince yourself of that. I hope you'll be able to do that, though. I'll see that fairly straightforwardly. So my forces are T plus mg sine theta. And that's got to equal m times mass times acceleration. And in vertical circular motion, this is always going to, any circular motion, this is going to be mv squared over r. Now my v, I'm getting a little bit careful about my notation here. I don't want to use v because I've been using it for something else in the earlier part of the question. So this is now a y, isn't it? So that's my squared over r. And now the radius of this circle is 0.5. I'll just put that r as a value straight in there. I hope you're okay with that. And so a little bit of rearrangement of that. What I'm interested in really is some kind of expression about the tension. So what I've got here, I've got something divided by 0.5, though, well, that's the same as multiplying by 2, isn't it? So that term becomes 2my squared, and then I've got to take the mg sine theta term from the other side. So there, now I've got an expression for my tension. But I've got an expression for my y squared just a little bit further up there, so I can now substitute for that expression for y squared as well, and that's going to get me my t in terms of u and theta. So instead of 2my squared, now I'm going to have 2m, and then all of that y squared expression is going to go in there, u squared minus 3g minus g sine theta. And then we've got to subtract the mg sine theta as well. And in order for it to complete circles, we want t greater than or equal to 0 when theta is equal to 90 degrees here. T greater or equal to 0 when theta is equal to 90, so the small circle has reached the top there. So we want this right-hand expression to be greater than or equal to 0 when we substitute 90 in place of the thetas there. So that's just telling me now that I want 2m u squared minus 3g minus g sine 90. Well, sine 90 is 1, so that's just a g. And then minus mg sine 90 again, that's another 1 there, so I can just have that as g. We want that to be greater than or equal to 0. And then that gives us a relatively straightforward inequality to solve. The m's cancel out. We can rearrange it fairly quickly to get ourselves with something that says u squared has got to be greater than or equal to 9g over 2. And then we can work out what our minimum value for u is.